Oh, yeah. You need a differential equation and you need it now. And you probably need to verify that the solution we've been using over and over again is actually a solution to that differential equation. So let's take a look at this thing. And maybe what I'll do is I'll start with showing you a physical example of this problem here. All right, and so where do I want the spring? I want the spring on this side. So here's the situation. This is marked off. The black strip is about 5 centimeters. This white strip is another 5. So notice that's 10 centimeters. So if you need the scale here, I think this thing's about 500 grams. And I honestly don't remember what the spring constant is here. But this is kind of what we're talking about. You could see here is a mass oscillating back and forth. All right, we'll get it going here. Now you can see I'm not very good at this, but this spring is actually compressing a little bit and then stretching. So this, right here, for a horizontal system, this is the unstretched, right? There's no tension on here. I'm not holding it at all. So this particular length is the unstretched, and I'm going to line that up right here. Oops. This matches my coordinates. So this is 50 right here. This is 50. Okay, so that just helps me. Now, as I'm cranking this thing out, so we could set this 50 centimeter mark as my equilibrium position for a horizontal mass spring, not for vertical, because the unstretched is the case where there's no net force. This thing is in equilibrium. So for horizontal mass spring, unstretched and equilibrium positions are the same. Not true for vertical. Now I could stretch this and watch it go back and forth. We see it compress and stretch. So our goal is to try and derive a differential equation for that weirdo situation. Go back to the board. All right. So here's where I put my red marker. So I guess I need that red marker. That was one of the things I just said. It is not true for vertical case. All right. Now, in this case, I'm going to use the following coordinate system, right? I'm going to say X is to the right and Y is up. I'm going to choose my acceleration to be to the right. This is a standard way of doing it. You might be saying, dude, we just saw you pull this thing to the right and accelerate it to the left. You're absolutely right. However, I argue we've seen that the acceleration can take on both positive and negative values. So think, right at this point, it is accelerating to the right with a negative value. A negative value to the right is equal to a positive value to the left. And this distinction is kind of annoying for students. We're used to drawing free body diagrams where we say, oh, hey, man, there's a spring force this way, and there's a normal force this way, and there's mg. But you got to remember, these are force magnitudes. And so a lot of times what we would do is we would align our coordinate system this way and say A is this direction. However, if we want this to relate to plots of xt, vt, and at, it helps to use a standard coordinate system, because when we look at these plots, you're thinking, hey, man, a positive value here means I'm to the right. A positive value here means I'm moving to the right. A positive value here means I'm accelerating to the right. A negative value means accelerating to the left. So this is how you make the free body diagram match up to your plots. And that's kind of a subtle thing. Again, we oftentimes use this type of free body diagram. Everything is a magnitude, including the acceleration, in this type of free body diagram. That's not what we're going to do here. All right. We expect a negative value for acceleration when x is positive. So in this case, I'm going to call this x, and that's going to be the position not distance. X is a position, and this is the acceleration vector. X component. Is that legible? Yeah, it is. Okay. All right. So maybe I'll just write this out. All right. So X is now a position, not a distance. So I'm going to write the force equations, or well, I guess I should draw a free body diagram. Right? In this case, I'm going to say there's a force to the right from the spring, and I'll say that's a force vector equals negative K delta X. So in this case, if delta X is positive, the force ends up being a negative value to the right. Super goofy, right? Kind of strange, but this is how this differential equation is defined. So we've got a normal force up. We've got mg down, and we're talking about this. That's a negative j hat. So now I'm kind of using these whole things as vectors. If I want to use this equation with the minus sign, right, I have to think about delta x as a positive. I want to go a little bit more in depth on this one. This is negative k x vector minus x unstretched. You always use unstretched in the force equation. That's true whether it's horizontal or vertical. What's special is in a horizontal problem, we can set this position equal to 0 because for a horizontal, the equilibrium and unstretched are the same. We can then drop this out. In a vertical, we had to base everything off the equilibrium position, right? The oscillation was relative to equilibrium. Now it's relative to the equilibrium, which happens to be the unstretched. All right, so just rewriting this thing, notice we could write this a simpler way. Negative K X, where X is the position. Now in this case, we oftentimes have an implied I hat on things, whatever, but the main thing that you need to focus on was it's a negative force to the right because X is to the right. X is a positive value here. All right, so this makes sense. Rewriting this thing, or writing the force equation, force from the spring equals m acceleration. Now, this is the x direction here. All right. So if I wanted to, I could maybe rewrite this as minus k x in the I hat equals mass times acceleration in the I hat. If x is a positive number, this is a positive quantity, this is negative, which makes a negative. Again, this makes sense. If we stretch it to the right, you get a negative acceleration to the right. Okay. These I hats drop out, and we get, let's see, x equals negative m over k times the acceleration. All right. All right, so let's leave it at that. Actually, let's maybe rearrange it the other way. I guess either way is fine. You could say it's negative k over m times x equals a. That is a differential equation, but it doesn't quite look like it. Let's remind ourselves what a is. So here's x. Is some function. What is the derivative of x with respect to time? That's velocity. I'm going to call that x dot. Beware. Dot and prime aren't the same thing. A dot is a time derivative. So if I said dx like this, dy dx is y prime in your math class, dy dt is y dot in your math class. A prime indicates an x derivative, a dot indicates a time derivative. All right. So in this case, one derivative with respect to time is that. What's the acceleration? Well, that's the time derivative of the velocity, which is d dt of x dot. That's x double dot. Okay. So that's just the notation we use because it just gets messy if we don't do it. All right. So time derivatives. So I could now rewrite this thing down here. Let's keep this color code going. Notice I get and this is how you'll often see it written, certainly as a junior and senior, but by the time you get to the end of your sophomore year, this is usually how we're writing things. So if you don't like that and you would prefer to write it like this, that's fine. But I just think this looks a little bit prettier, so I use that shorthand notation. And just being straight with you, I'd be fine writing either one of these if I said write the differential equation and you did it this way, full credit on the test. So this is just less to write. Okay, so that's the claim. Now, or that's the differential equation. So this is called the differential equation. It's an equation that includes a variable and derivatives of that variable and some constants. Now, watch what happens here if we use this solution. We've already seen the velocity is minus omega naught x max times cosine omega naught t plus phi. Is that fitting all on the board? Just barely. Right? We've seen that the acceleration, or x double dot, is minus again, just take the derivative of the function, you get a negative. Oh, I screwed up, didn't I? That's a sine function. You take the derivative of cosine, you get a sine with a negative. You take the derivative of what's inside and omega naught pops out. You take the derivative of sine, you get positive cosine, but there was already a minus sign laying around. So let's see what happens when we plug this junk in to this differential equation. We get minus k over m times x, which was x max. To be clear, x means x is a function of time. Remember, as this thing oscillates, x could take on different positions, positive or negative. X is a function of time, so is its derivative. Right? X max and now A. Now think, this has to be true for any point in time. Notice what cancels out. Oh shit. A and X max are the same thing. Ah, well, shoot. I should have written this as X max. I apologize. The amplitude and X max are the same thing. They cancel out. The cosine function cancels out. And the minus sign cancels out. What are we left with? Omega naught squared equals k over n. If you remember in one of the very first videos, I said the resonant frequency, and by that I mean resonant angular frequency, is the square root of k over n. So this is a solution. Could I have used sine up here? You bet. But remember, cosine function and sine function are basically the same function, if you just use a phase angle of 90 degrees or negative 90, depending on which ones you're using. But basically, you could shift the phase by 90 plus or minus and change a cosine function to a sine function. So another solution would be x equals x max sine of this garbage. Whatever. All right. A quick note on the word frequency. You heard me say, the frequency is the square root of k over m. That's not true. The angular frequency is. But so often we're going to use frequency and angular frequency. Usually you can distinguish those by the units, or if you're talking in a presentation and you say frequency for this and you show it and use the right units on the screen. I'm going to be doing the same thing all the time where I call omega a frequency. Strictly speaking, we should be saying angular frequency. On test day, I'm pretty good about saying the right words, okay? So if I ask you for frequency on the test, I'm looking for F. If I ask for angular frequency, I mean omega. Okay. All right. I think that's about it. I will say one other thing. Let's go to the board. Maybe I'll just squeeze it in here. I don't know. I'll go over to this board. So this is extra. If you want to stop the video now, you can. If you want to see this tiny extra bit, it's 2 minutes. Okay. So these are the two forms of the general solution to most common forms of the general solution to x double dot equals minus omega naught squared x, right? Or in this case, omega naught equals square root of k over m. We've seen one. In your math classes, they'll often say it this way. So I just want to point out a linear combination of sine and cosine will produce a correct solution, right? And there's a relationship between the constants a and b and the constant x max and phi. And I derived it once and made a spreadsheet. I don't know where that is. If I find it, I'll give it to you, but it's not really that important. It turns out in most physics applications and engineering applications, we tend to prefer one trig function with a phase angle as opposed to two trig functions. Not always true. There's exceptions to everything, but those are just the two possibilities for the general solution. Again, you could use sine here, but I think most textbooks tend to use cosine here. Not always true. For us, we're going to use cosine for oscillations and sine for waves in the next chapter. And so that's how we can kind of keep it straight on the equation sheet. All right, I'm really done with that now.